Hello, welcome back to my lecture. So, we have already seen how van der Waal brought new ideas into the mix in our previous lectures. We saw that there are certain corrections to be made. We saw the correction particularly to the volume through the constant B, and also a correction to the pressure through the constant A. And we applied it to Andrew's experiment on carbon dioxide, which gave us critical behavior of a gas or for example carbon dioxide gas. So we understood that there is a particular temperature known as critical temperature, pressure called critical pressure, and which is happening at a critical volume, which is referred to as a critical point, right? Now we know these definitions. Now our aim is to dig deeper into these critical constants and see what we can understand. So what we require is an expression for these quantities so that we have a general framework in which we can understand this particular behavior. Therefore, our next aim is the estimation of critical constants. Now, for that, we go back to this particular graph and we concentrate on the main curve here, which is the green curve, the critical curve, which I have isolated and drawn here like this and marked ACB, with C being our critical point. Now, we are going to bring out our toolbox, which is mathematics, the language of physics. Here, I have adapted an image from Wikipedia which can be used to understand this particular critical behavior. We are concerned about this point C, which I have marked here. I called it critical point before in the context of Andrew's experiment on carbon dioxide and the graph obtained from that particular experiment. But mathematically, such a point is referred to as an inflection point, which is x is equal to x0. What happens on the left side of x0, the curve has a particular shape. It shows a concave up behavior, and on the right side of x0, it shows a concave down behavior. So to understand this a bit more clearly, I have drawn this. I have extended both curves to both sides. So now it is clear what is meant by concave up and concave down, right? I have completed each halves. We get two curves and these two curves intersect at this inflection point x0. Now we are going to study what are the peculiarities of this inflection point which corresponds to the point C in our graph. An inflection point is where a function's concavity changes. Now this behavior is defined by the first and second derivatives of the function. Let us focus on the second derivative f double dash x, which is the primary tool for identifying these inflection points and describes the concavity of whatever original function we have, f of x. Let's call it f of x. What happens before the inflection point? The sign of the second derivative is of one value. That is, it can be positive, which indicates concave up. Now, what happens at the inflection point? The second derivative is typically 0 or it is undefined. It doesn't have any particular sign associated with it. After the inflection point, the sign of the second derivative changes, that is from positive to negative, indicating concave down. So, the first derivative. Now, what is the role of the first derivative? The first derivative indicates the slope of the function, right? That is something we are very familiar with from our earlier classes. Y is equal to, m is equal to m, which is a slope, which is equal to dy by dx. That is the first derivative, right? So this slope, we also know that a slope is the tangent drawn at that point. Now, if you draw a tangent at any given inflection point, we get a line which is parallel to the x-axis. What is the slope of a line which is parallel to the x-axis? It is 0. It does not have any slope. It is parallel to x-axis, right? So, here the slope, that is m, will also be 0. So, now we have two additional information regarding this particular point C. What is that? The first one is d square p by dv square is equal to 0. And this is at a constant temperature because we are talking about our particular curve which is at that critical temperature, right? So d square p by dv square is equal to 0, which shows that at that inflection point, the curve is neither concave up nor concave down. It doesn't have any sign. It is stationary. It is a stationary inflection point. And also dp by dv is equal to 0, which shows that at the inflection point, if you draw a tangent line, it will be parallel to the x-axis, which states that its slope is equal to 0, which means that dp by dv is equal to 0. Why dp by dv? These are the variables that we are dealing with, right? Our curve is a function of p and v, right? So that is what we have. These, with arming ourselves with these two conditions, we can actually derive expressions for critical temperature and critical pressure. Now if we have these two values, then we can apply it for any gas. We don't have to repeat Andrew's experiment for all the available gases. We can theoretically, we can ideally apply it to other gases. So now we are going to derive our critical constants, expressions for critical constants. So what is the first step? We write what is the van der Waals equation. Now, what is our corrected van der Waals equation? We have, so right now we are going to estimate the critical constants with whatever we have discussed before. So the first step is write the van der Waals equation. Now we know what the van der Waals equation is, but we will write it for 1 mole. Okay, so if it is 1 mole, we have P plus A by B square into V minus B is equal to RT. So this is our van der Waals equation. Now I want to rearrange it a little bit. So P plus A by V square is equal to RT by V minus B. Now if we take A by V square to the other side, we have P is equal to RT by V minus B minus A by V square. Okay. Why do we do this? Because we have two conditions, dp by dv and d square p by dv square. We need to find out. So we need this function to be in the form which facilitates that differentiation. So that is why we have written it like this. P is equal to RT by V minus B minus A by V square. Correct? Okay. Now what is the next step? Apply the critical point conditions. What are the critical point conditions? dp by dv at constant temperature is equal to 0 and d square p by dv square at constant temperature is equal to 0. Let us proceed to do that, which is differentiating once and twice. So we have what? P is equal to RT by V minus B minus A by V square. What is dP by dV? It is at constant temperature, so RT will be treated as a constant. V is the only variable here. So we have, what is 1 by V? Differentiating 1 by V, we get minus 1 by V square, right? V minus B the whole square. Now, what is the second term? Minus A is a constant by V square. So 1 by y square. How do you differentiate it? That is equal to minus 2 by V cube, and we have the constant A. So what do we get? Minus RT divided by v minus b the whole square. Minus and minus will become positive. 2a divided by v cube. So this is dp by dv. Now the next step is to find out b square p by dv square. That is equal to, you have a minus here. We will write RT here, which is a constant. So 1 by v minus b the whole square. That is what we are differentiating. B is treated as a constant. So just like the second term in our previous equation, we will get a minus 2 here and v minus b the whole cube plus. Now 2a is a constant and we will differentiate 1 by v cube. So there is a negative 3 by v cube v raised to 4. So what is it? The final expression is 2RT divided by v minus b the whole cube minus 2 3s are 6a by v raised to 4. So we get dp by dv and d square p by dv square. So these are the expressions that we have just derived. Great. What is the next step? Now the next step is we have to substitute v is equal to vc, t is equal to tc. Why do we do that? It's just a simple thing because we are trying to find out the critical volume, critical temperature and critical pressure, right? So in order to understand that, we will just replace wherever we see V as Vc and wherever we see T as Tc and equate it to 0. So what is our first term? Minus RT by Vc minus B the whole square plus 2a by Vc cube is equal to 0, which means taking the negative to the next side, RT by Vc minus B the whole square is equal to 2a by Vc cube. What did I do? I took RT by Vc minus B the whole square to the other side, to the right hand side. Therefore, the negative got cancelled and I just flipped it. That's all what I did. And for the next term, d square p by dv square is equal to 0 implies 2RT divided by Vc minus B the whole cube is equal to 6a by v raised to 4. Sorry, Vc raised to 4. T is also Tc. Okay. Here also Tc. Sorry for that omission. Now, what we do is we divide these equations because both have Vc minus B the whole square and RTc on both sides, right? So we divide the equations to solve for Vc. Okay, so that is the next step. How do we do that? So divide the equations to solve for Vc. We have dividing the left hand side. RTc will get cancelled. 1 Vc minus B will remain. Let's divide it. RTc by Vc minus B the whole square divided by 2 RTc by Vc minus B the whole cube. What does this mean? RTc will get cancelled. This entire Vc minus B will go and this will go upstairs, right? Vc minus B divided by 2. On the other side, what we have, 2a by bc cube divided by 6a by vc raised to 4, right? So that is equal to 2 will get cancelled, a will get cancelled, this is 3, vc, this will get cancelled, this is get cancelled. So what we get is vc by 3. So bc minus b by 2 is equal to vc by 3. 3vc minus 3b is equal to 2vc, which means 3vc minus 2vc, vc is equal to 3b. Great. So we got the expression vc is equal to 3b. Now back substitute to get tc. If vc is equal to 3b, then you do something, you choose whichever expression is easy for you. Let's see. So now that we have got what is the value of vc, we can back substitute to get the value of tc. So pick an expression which is easier for you. Let's pick up the first expression. rtc by vc is equal to 3b, right? 3b minus b the whole square is equal to 2a by bc is equal to 3b. 3b the whole cube. That is rtc by 3b minus b, 2b. 2b square is equal to 4b square is equal to 2a by what is 3 cube? 3 cube is 27. Remember, don't write 3 cube is equal to 9, which is a common mistake that sometimes students make. 3 cube is 27. B cube. Now we get cancel b here. Then keeping tc on one side, we get the expression 4 2s are 8. 8a divided by 27 rb. Sorry, that is 27 rb. So now that we got that, use van der Waals equation to get Pc. So you can substitute in any of these equations to get Pc. So we have to back substitute to get Tc, and in order to get Pc, we have to use the van der Waals equation. So which is the van der Waals equation? The first equation, this one. P is equal to RT by V minus B minus A by V square. Now we know the expression for T, C and VC. Just substitute it. Then we get PC is equal to R by VC is 3B minus B into TC is 8A by 27 RB minus, what is A is just a constant, and here V is equal to 3B the whole square. That is equal to R by 3B minus B is 2B into 8A by 27 RB minus A by 3 square is 9B square. So here is one mistake that students might make if you don't have enough practice while you are writing an exam, or whenever there is a crucial moment in which you have to derive this. The mistake that you make is sometimes 3 cube is 27, 3 square is 9. So you always have to remember that. So that is what we will be doing here. So we have R by 2B into 8A by 27 RB minus A by 9B square. In here we can just cancel out R, and 2 and 8A will get cancelled out, and the resulting equation is 4A by 27b square minus a by 9b square. 8a by 27b square minus a by 9b square. This is PC. So what we have is PC is equal to 4a divided by 27b square minus a by 9b square. So what is the LCM? That is 27b square. So we have 4a minus 9 has to be multiplied with 3 to get 27. So we multiply that with the numerator as well. So 3a, which is a by 27 b square, that is PC. That's it. This is the final result. You have VC is equal to 3B, TC is equal to 8A by 27RB, and PC is equal to A by 27B square. So whatever you see on this left hand side is this blueprint. So whenever you try to study it, or whenever you try to study any derivation, make some key points, remember these key points, get enough practice so that you don't get confused while deriving it, and then whether it is an exam or an interview or for higher studies where you will be using these sort of mathematical equations to derive or solve an equation or solve a problem, you will be able to approach it in a methodical manner. So that's it. Next, we will see how close the van der Waals equation is to the real gas behavior. Yes, I am saying that even with all these corrections, the van der Waals equation is still not adequate enough to give you the exact real gas behavior. Now, if you go for higher studies or if you are working in this sort of physics later for research, you will encounter many other approximations, many other corrections that will get you closer to the real gas behavior. So, let's just understand the very first correction that we have studied, that is the van der Waals correction. That's it. Thank you.